Now it says that the XOR total of an array is defined as a bitwise XOR of all its elements, or 0 if the array is empty, which means that I have to do a XOR of all the elements and then I have to take the add up. So for example, the XOR total of the array this is 2 XOR 5 XOR 6, which is 1. Now I have been given an array nums. I have to return the sum of all XOR totals for every subset, which means for this array which was 2, 5, 6, I have to generate all the subsets, and then out of all those subsets I have to basically add their XOR totals. So for example, for this 256, one subset is 256 itself. Okay, I got the XOR value. Another subset can be 25. I will get the XOR value whatsoever. Then I will have to add up all the XOR values. That will be the sum, and that is my answer. So you can see, for example, in this case, I will generate all the subsets, and then while generating the subsets, I know I have to do a XOR of that specific subset and then add up the XORs of all these subsets, and that's my answer. So you know your basic task is to now generate all these subsets. We have already seen in our backtracking crash course, we have already seen multiple ways. Again, in this we have seen how to generate these subsets. If you don't know recursive way to generate, or basically backtracking way to generate the subsets, I'll go and highly recommend watch this video. But we know that in our bit manipulation crash course also we have seen that mask is actually used to generate the subset. If you don't know what masking is and how to generate these subsets out of that, I'll highly recommend go and watch this video. But now for a quick recap, how mask is used is that we know that we have an array of size n. N is 3 in this case. So I know I will have 2 raised to power n number of subsets. So I will take use of my bit manipulation and I will generate all the numbers from 0 to 2 raised to power n minus 1. So these are all the numbers from 0 to 2 raised to power n minus 1. This actually shows me, okay, what 0 here means. 0 here means that this specific index value is not included. 1 here means is this specific index value is included. So if I take this again, this is now called as mask. I went on and told that mask will be from number 0 to number 2 raised to power n minus 1. Now this is a specific mask. What this mask is trying to say me is that first 0th bit will come, first bit will come, second bit will not come, which means 0th index will come, first index will come, second index will not come. So if I have my nums, saying as if I take the same nums 5, 1, 6, so I can simply say that 0th index will come, which means 5 will come, first index will come, okay, 1 will come, second index will not come, 6 will not come. So this is a specific subset. And again, I will try it for all the subsets. So you can simply see, to generate all these masks, I can simply do a for loop. For mask is equal to 0, mask is less than 2 raised to power n, and then mask plus plus. So I'm trying for every mask, and for every mask I have to get to know, like I have to know that which actual element from my nums I have to take. So I will do a simple 1 left shift I to just know that at what index I should put my 1 for the specific mask, and then AND with the mask. Again, if you don't understand this, I'll highly recommend go and watch this video. One crash course completely enough for you for bit manipulation. Now, so we know that to check if that specific element of nums is present in that specific mask, I will apply this operation, and accordingly I will do a XOR of that specific nums of I, which validates this condition. And ultimately this is for one mask. I just have to add up for all the masks. So what I do, that I have taken this XOR total is for one mask, one specific mask, and I have to add up for all the masks. So I take up the summation, and that is my answer. So you see that this will go for loop 2 raised to power n. This will take a O of n time. So my total time complexity is O of n into 2 raised to power n. And space, as I can see, I am using no extra space. So space is O of 1. This is more optimized than that of recursion, because in a recursion you will use a recursive depth space, which will for sure take a O of n space. But we know to generate all these subsets, bit manipulation technique is the best. Now coming on to the most tricky approach, which is, can we improvise it much more? For sure, in an interview it is very highly impossible to think of if you don't know this approach already, because it needs a very big example and dry runs to actually make sure that things are actually working, and it's not that easy to come up in an interview. But still, we will see that how it can be solved in O of n time. Now, taking the same example, 516. Again, I'm taking example, but I will prove everything. So n is 3. Now again, what I did, what my earlier approach was doing, my earlier approach was generating all the masks. Okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are all the 8 masks which my earlier approach was generating, a 2 raised to power n number of masks. Remember, now what I was doing, for every mask I was going and checking the contribution of that element, which means 0th element is included. This element, again, I have indexed, if you know that these bits are from right to left, right? So this is the 0th bit, this is the first bit, this is the second bit, right? So I have, for your like simplicity, I have indexed my array element from end, right? So no worries on that part. It is just, again, end or start both will remain same. It's just for your simplicity to understand the example itself. Now it simply says that the no element is included, so I have included none of the elements. 516, no element is included. Okay, XOR value is 0. Make sure this is the XOR value which you were doing in this for loop. This is the XOR value which you were doing in this for loop for all the n elements. Okay, here it says that the element 6 is included, rest of the elements are not included. So I will include the element 6, I will include the element 6, and rest of the elements I have not included. Now this is a XOR value. Okay, same way in here I will include the element 1, rest I will not include. Okay, this is the XOR total, and here I will include my 6 and 5, sorry, 1 and 6, 1 and 6, I will not include my 5. Okay, this is my XOR total. Again, here I will only include my 5 and I will not include these elements. Okay, this is the XOR total. Here I will include these two I will include, I will not include this. Okay, here I will include these two I will include, I will not include this. Okay, you can see here I am including all of these, which is I am including 5, 1, 6, 5, 1, 6, and then I'm doing a XOR, and then this is the result. So now I have got the XOR totals. So what I was doing, I was simply adding up all these XOR totals. So this, and this. I'll simply add these XOR totals. So if I write all of them, it is a 0, 0, 0, it is a 1, 0, 0, it is a 0, 0, 1, it is a 1, 1, 1, and if it is a 1, 1, 0. So I just wrote all of them. All these 2 raised to power n XOR totals I wrote, and then I just simply added them up, because I want to get the answer. So I did addition of these XOR totals. So I will just simply add them up. If I add these up, I will say, okay, I have won 4 number of times. So for sure 4 into 2 raised to power 0, because it is at the 0th bit, right? Okay, now this is at the first bit. So 2 raised to power 1, but how many times? 1, 2, 3 and 4. Okay, 4 times. Okay, then at this location it is 2 raised to power 2, but how many numbers? 1, 2, 3, 4, again 4. Okay, 4 into 2 raised to power 2. Okay, it seems like some pattern, but what it means? So it simply says that, okay, I have some 4 which is repeated, and I have some numbers which is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2. So this is what we saw for n is equals to 3 and nums of 5, 1, 6. So with this viewing of example, can you even figure out that, well, like, first question is, what does it even mean? That's your question. That's your you will say, Aryan, what does it even mean? For other YouTubers, what they will do, they will just show you, okay, this is half of the number of subsets and stuff. Bro, hold on, it is never true. How do you even prove it? So we never know that if I have an n equal to 4 and when my nums are something else, then what will be my answer? Let's see that. So if I go and ask, let's take a step back and let's reverse engineer what we have written. So if I know my total number of subsets were 2 raised to power n, right? Now if I'm just asking you, okay, with this viewing of the example, let's see the involvement of every number. So I know my numbers were 5, 1 and 6. Okay, let's hold on and let's see the involvement of 5. As you can see, involvement of 5 is in white, right? And then I will see the involvement of 1. Okay, it is in green, right? Now, okay, let's go and check the wherever my 5 was involved in doing the XOR operation. So again, remember, it is white, right? Involvement of 5 is white. So I went on and checked where all, as you can see, 5 is not involved here, 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 5 is involved here. As you can see, 5 is involved here. Okay, 5 is involved, and because of that involvement itself, we can simply see on doing the XOR operation, my 5 is 101, right? 5 is 101. So this 1 was contributing here. The 1 was contributing here also. Oh, my 5 was contributing in the answer, because this, if I show you, this is the XOR total which you have ultimately added up in your answer. This is actually your addition thing which you are doing, right? So you added up this XOR total in your answer. Okay, my 5 entirely contributed to my answer. Okay, let's see where else my 5 was being used. So I will go down and I will see, okay, 5 was also used in this specific mask. So if I just ask, okay, 1, again, 5 is 101. So this specific one, this specific one of my 5 is, okay, I had copied it up, but this specific one of 5 was not copied. So is it that I'm not using all the ones of 5, which means if my 5 is a 101, so technically with this representation, it feels like that this specific one of 5 would be used 4 times, but it doesn't feel like, because okay, I am using my 1 here, but this specific one of 5 is not used. Okay, no worries, let's see the example. So here also my 5 is being used, so I'll see the contribution. Okay, 1, okay, it is in the answer, this specific 1 is in the answer, but this specific 0th bit of 1 is not in my answer. Oh, okay, no worries. Let's see, let's see this specific one. So 5 contribution 101. None of the ones contributed in the answer of 5. Okay, so we firstly, one very basic thing which you should have seen so far is that you had 8 subsets. If I zoom it up a bit, you had 1, 2, 3, 4, 5, 6, 7, and 8. You had 8 subsets. Out of these 8 subsets, in 4 of them, my 5 gave the contribution. My 5 gave the contribution. I'm not saying that in the answer he was present or not, which means in the answer my corresponding 1 of 5 was present or not. I'm not saying that. I'm just saying the 5 gave the contribution, which means 5 was here, 5 was here, 5 was here, 5 was here. Okay, is it Aryan always sure? Let's see with the other, maybe we can check with the 1. So again, we can check with 1. I can see the involvement of 1, how many times 1 is occurring. So I can simply see that, okay, 1 is not occurring here, 1 is not occurring here, 1 is occurring here. Okay, and also he contributed in the answer. Okay, 1 is occurring here also, he also contributed in the answer. Okay, now where else 1 is occurring here also, but here he did not contribute in the answer. Okay, I'm just saying the involvement in the number of subsets. Okay, 1 is also occurring here. So again, if I show you, this was a green one is occurring 1, 2, 3, 4 times. So this is very evident that every number involvement in the mask will be 4, which is, if I say that if I have n numbers, I will have 2 raised to power n number of subsets. Then 2 raised to power n number upon 2, right? Upon 2, 2 raised to power n upon 2 number of subsets will be there, where a specific nums of I will be involved. Now again, if I show you, this will be nothing but a 2 raised to power n minus 1. So this is the involvement of a number. I'm not saying it will contribute to the answer. Now, answer is this specific thing. This is the answer. I'm just saying the involvement of a number, nums. Now, if I show you, so you realize by seeing this white, which was for the specific number 5, you can simply see that if you see the answer contribution is only because of this first. Again, I have numbered this. It is the first involvement, it is the second involvement, it is the third involvement, it is the fourth involvement. So I can simply see the actual contribution for 5. It came in the first involvement. Okay, first involvement. So I can see that I have 101, which is this specific thing. Then I had 011, 011. Okay, the 5, if you see the 5 is 101. So this specific bit of 5 actually contributed only in 2 cases, because the other cases, this specific bit never contributed, right? Again, this specific bit never contributed, but I can simply see this bit of 1 contributed. So I can simply see that the 1 bit contributed. So technically it feels like that any bit is contributing, any specific bit is contributing roughly half times of its involvement. Okay, but do you see one thing? Why he could not contribute to the answer? Why my number 5, as you can see, number 5, this specific bit contributed to my answer. Okay. Number 5, this specific bit contributed to my answer. Okay. But number 5, this specific bit, he could not contribute to my answer because here it is 0. He could not contribute to my answer. Why he could not contribute? Because he could not contribute because of the 1 right here. Oh, yeah, it makes sense. Then if I see the other involvement of 5, which is the third one, I can simply see 1 could not contribute to my answer because of this specific 1. Make sure whose 1 is this. Make sure whose 1 is this. Okay, no worries. Then I will simply can go about and say, okay, 1 was involved here. But here also, I can simply see that the 1 right here was not involved in my answer because of the 1, because of this is the 1 because of he could not be involved in the answer. He could not contribute in my answer because of this row. And same way, this specific 1 could not contribute to my answer because of this row, which is last row, which was 6. This is 6. This is 1. Now, if I look back, same thing for 1. I can say the same thing for 1. For 1, he contributed to my answer. Okay. For 1, he contributed to my answer. But if I see the other case, for 1, he could not contribute to my answer. Why? He could not contribute to my answer. Why? Because of the other 1 came in picture. So we realize that it is okay that this, see again, remember, this 1 is for 5, this 1 is for 1, right? This one is for 5, this one is for 1. Now it is very evident that when my 5 wants to contribute to my answer, in half of the cases, 1 is actually taking away its contribution by involving himself. As soon as 1 involves himself, the contribution of 5 becomes 0. So, okay, basically this 1 is taking away the contribution for 5. And I can say the same thing for 1 also. 5 also, that 5 is taking away the contribution of 1. But then if they are taking away the contribution of each other, they are also giving the contribution separately. As you can see, 1 is giving the contribution separately. How many times he will take away the contribution? How many times he will take away the contribution from 5? Those many number of times he will also give the contribution. That is, how many times they are taking, they are also giving back. So, although the contribution of 5 is only here and here, the contribution of 1 is only here and here. The other, again, I showed you the involvement of every nums of I is 2 to the power n minus 1 number of times. But 2 to the power n minus 1 number of times, it is the involvement of a number which is 5. But their contribution in the answer is kind of snatched away by the other bits. But if they are snatching away the other's contribution, they're also giving the equal number of contribution in the answer. Ultimately, I'm only concerned about the answer. So I know that ultimately, this is the total bucket. Let's say 5 is contributing something and he wants to, let's say this is my total bucket, 5. 5 could actually involve himself like this much. But then 1 came and took away its involvement. Let's say 3 came and took away its involvement in the answer. But still, they will also contribute the same thing. If they are snatching away, if the 1 is coming and snatching away this portion from 5 to actually contribute to the answer, 3 is coming and snatching away this contribution, then they will also give the same amount of contribution to the answer. So like 3 will fill this, 1 will fill this. So for me, this is the total involvement which will be filled no matter what. So in total 1, like again, I'm saying that 5 will also have 101, he will also have 001, sorry, 001, he will also have 011. So basically I am referencing this specific bit. So this specific bit 5 could have said for this specific bit, my involvement could have been 2 raised to the power n minus 1. But then they will say, I will snatch away some contribution from 5. But still, they will give the equal contribution to the answer. So ultimately, in total, we can easily say that I can have the contribution in total as 2 raised to the power n minus 1, because this is the only bucket which I have, right? And thus ultimately, this is the contribution. This is the contribution of every bit, which can be there. So I realized that this actually answer says that 4 is the contribution, which is 2 raised to the power n minus 1. And then this says, okay, I have 1 at this place. I have 1 at the first bit. I have 1 at the second bit, which means if I take the example of n equal to 4, then my nums is, let's say, 1, 8, 2, and 3. I can see that 3 can contribute, like 3 can have at the 0th bit and the first bit. He can have at the only first bit. He can have at the only 0, 1, 2, 3, third bit. He can have only at the first bit. So I can easily see that this bit, which is the second 0, 1, 2, second bit, is not filled by anyone. Second bit is not filled by, he is not filling it, he is not filling it, he is not filling it. So second bit is a bit which is not filled by anyone, which means it will always remain empty. So if I show its representation, I can simply say that, okay, I know that all the other bits are filled, which means if I have this xxx, I know this bit is filled, this bit is filled, this bit is not filled, this bit is filled, because 8 is filling this bit, others are filling this bit. And again, if someone is taking the contribution, he will also give the contribution. So I can easily say that I know the contribution in total in the answer will be 2 raised to the power n minus 1 for everyone. And then I just need to get, okay, this bit will be there, which means a 2 raised to the power 0 will be there, a 2 raised to the power 1 will be there, a 2 raised to the power 2 will never be there because it was 0. No one even contributed ever for a 1 for this specific location. And then I will have a 2 raised to the power 2 as my answer. So this will be my answer. But Aryan, how to get it? Okay, this is constant. If I know the array size n, so I know this is constant. This is constant. But what about this? Oh bro, this is just saying if at that location any of the bit is present or not. Any of the bit is present or not, because we realized even if I have one bit, which means even if I had the number 8, if you remembered, which is 11000, so this will take all the contribution. But if I have a case like, for example, if I have a case of 10 and 1, if I have a case like 10 and 1, which means it is 2, it is 3, then for this specific bit, the contribution would still have been a 2 raised to the power n minus 1. But then he, like this, for 2, for the first bit, he would have tried to take all the entire contribution for him. But then for 3, first bit would have come in and took away some part for him, and then he would also have contributed the equal part to the answer, right? So I just want to know that if that bit is present or not at that location. So I just want to know if the 0th bit is there in the entire nums, if the first bit is there in the entire nums, if the second bit is there in the entire nums, and if the third bit is there in the entire nums. If you want to know the existence of a bit, you simply do OR operation. So what I will do, I'll do an OR operation of these numbers, which means 0001, 1000, 0010, and 0011. I'll do an OR operation saying this is 1, this is 1, this is 0, this is 1, just showing me the existence of every bit. Okay, 0th bit exists, first bit exists, 0th bit, sorry, second bit, he doesn't exist, third bit exists. This shows me the existence of every bit, and thus I will know the existence of every bit. Cool. The code is pretty simple. We just first take the OR of all the numbers to show the existence of what specific bit will be there, and then I just multiplied with 2 raised to the power n minus 1 for that specific OR, or basically for that specific existence of those bits, and that is my answer in O of n time. Cool. I hope you guys got it with the proper example and dry run for both the cases. We saw that how it is possible. Cool. Bye bye. Take care. I hope you guys got it. If you have not watched the bit manipulation crash course, I'll highly recommend. Please go and watch this. It will be very helpful for you. If you have not watched The Scam Happened With Me, go and check the link down below. It was very bad, but yeah, that was a good lesson for me. Bye bye. Take care.